All right, in this video we're going to compute some iterated integrals, and to start let's look at this integral here in green and notice the order of integration. The inside variable here is x and the outside variable is y. Okay, so writing the integral in this form where I put the inside integral in parentheses for emphasis, okay, we're going to integrate with respect to x by holding y, the outside variable, constant. Okay, this is really the same kind of thinking we applied in computing partial derivatives. To integrate this function with respect to x, you hold y constant. This then will result in an expression that depends on y only, okay, not on x anymore. Then for the outside integral, we'll go ahead and integrate that expression with respect to y, and then that will give us the value of our iterated integral. And likewise for this integral in purple where the order is dy dx. Okay, we will compute the y integral first where we hold x constant. That will give us something that depends only on x. Then for the outside integral, okay, we'll integrate that expression with respect to x, and then that will give us the value of this iterated integral. Okay, and recall from the last video, after we had defined double integrals in terms of the limits of Riemann sums, right, we said that that definition is not going to lend itself to a particularly easy computation. So we took a slightly different perspective and thought about computing a volume in terms of stacking cross sections, right? And that's exactly what these iterated integrals are doing. So these inside integrals are cross-sectional areas where we're holding y, or in this case x, constant. The outside integral then is stacking those cross-sectional slabs to fill out the volume of your solid. All right, so with that all being said, let's go ahead and jump into problem 1. And in A, we're looking to integrate the function 2x minus 3y squared. And the order of integration here is dx dy. And so to start here, I'm going to just write in this inner integral in parentheses. And then a note on notation here. So for the x integral, okay, the bounds here on the inner integral symbol, -1 to 1, these are referencing x. So x ranges from -1 to 1, and then for the y integral, okay, those correspond to the bounds out here. So y goes from 0 to 2. Okay, so let's go ahead and compute this inner integral with respect to x, holding y constant. So integrating 2x, that's going to give us an x squared. And then minus, well, integrating 3y squared, that's just really integrating a constant. So we're just going to pick up an x. So I get 3x y squared. And then we're going to evaluate that from -1 to 1. And then we have our dy. All right. Now, again, sometimes this can be a bit confusing. You don't have to write this in, but again, these limits are referencing x. So when we go ahead and evaluate, we're going to plug 1 in for x and then -1 in for x. Okay, so you might always want to be sure you're clear about what variable the bounds refer to. All right, so if you plug in 1 for x, we'll get 1 minus 3y squared. And then we're going to subtract from that what we get when we plug in -1, and that's going to give us 1 plus 3y squared. Okay, so then clean that up and notice the 1's drop out, and so I'll get minus 6y squared. And now integrating that, it's going to give us a minus 2y cubed, and we're evaluating from 0 to 2, and so that's going to give us a minus 16. Okay, great. How about part B? Well, here we're integrating the function 6x e to the 3y in the order dy dx. So again, I'll go ahead and put this inner integral in parentheses. And so now we're saying that y ranges from 0 to the log of 2, and x ranges from 0 to 1. Okay, so now I'm going to go ahead and compute. We're going to compute the integral of e to the 3y, right? 6x is just constant. And so to compute that, leave a little space here. So the thing we got to remember is that if I differentiate e to the 3y, I'm going to pick up a factor of 3 from the chain rule. So turning that around with an antiderivative, okay, if a is any constant, to integrate e to the ay, I'm going to have to divide by a. Right? Because again, if I differentiate that exponential, you pick up a factor of a, so this 1 over a is going to divide that a out. So cool. All right, so that's going to give us then integrating e to the 3y, 1/3 e to the 3y. And now we're going to evaluate this from 0 to the log of 2. We still have our dx. And then here, notice the 6x and the 3, that simplifies. And that's going to leave me with a 2. And I can go ahead and pull all that out. I'm going to go ahead and put the 2 out in front. So that's going to leave us with the integral from 0 to 1. And I have my x there. And now what I want to do is plug in the log of 2 and 0 into this expression, e to the 3y. Okay, so if I plug in the log 2, I'll get e to the 3 log 2. And then subtract from that, I'll get e to the 0, which is just 1. And then dx. All right, now the thing to notice is that this entire expression is just a constant. And in fact, we can simplify it. So using properties of logs, I can say this is e to the log of, well, 2 cubed, which would just be e to the log of 8. And then we're subtracting 1. And e to the log of 8 is just 8. So that's just 8 minus 1. That's 7. So this, in fact, is just equal to 7. And since it is constant, I can take that out front as well. And it's going to multiply that too, giving us a 14. And then we're integrating from 0 to 1 the function x, okay, with respect to x. And so that's going to give us what? X squared over 2, so 7x squared. Evaluate from 0 to 1, so the value of this integral then is 7. Okay. A little more challenging there. It's good to review some things along the way with regards to integration, but this is what we're looking at. All right, so now for the last part of this video, I want to point out an important case or a certain pattern that can show up from time to time with the form of an integral. So in particular with that last example where we had 6x times e to the 3y, okay, the integrand here is of this form where I have something that depends just on x times something else that depends only on y. And when you have this kind of integrand, you can actually split it up in such a way that you're really left to compute just two single variable integrals. And in some instances, maybe not always, but in some instances, this can actually really simplify our work. Okay, so here's the general statement. So if your integrand, again, is of the form something depends only on x, so say g of x times something depends only on y, h of y, then compute the iterated integral of this function. We can just split it up as this product of single variable integrals, okay? And so in this particular case, we could have just split this up as integrating the e to the 3y on its own and integrating the 6x on its own. And I'm leaving out a little bit of the details there on the exponential integral, but that has a value of 7/3. The second integral has a value of 3, and so their product is 7, which is, of course, what we got before, but it's just a slightly different way to get there. All right, so now why is this result true? Let's go ahead and prove it down here. So the first thing to note is that for the x integral, h of y is held as a constant. And so it can come out in front of the x integral. And so that's going to give us the integral from c to d of h of y. And then that h of y is multiplying the integral from a to b of g of x dx. And then we have our dy. But then the next thing to observe is that this integral of g, as we let x go from a to b, this thing right here is just going to be a number, right? It's just whatever numerical value this definite integral is equal to. So when it comes to this y integral, this thing here in green is constant, so it can come out in front of that. And that is the end of the proof, because we're saying now, bringing that out in front, this integral of g from a to b with respect to x is going to multiply that integral from c to d of our function h. And this is one special case of it, and again, we'll see it come up from time to time down the line. All right, that's going to do it for this video. Thanks.